something new to describe what's going on, and that's how all of this came about. Just like how vectors and all of their relatives, quaternions and so forth, were developed over years to meet the needs of the time. All right. So, you can define what is a differential form. Okay. Now, differential forms all have an order to them. It's a number that indicates, that describes the type of form that you have. First, the simplest form of all is a zero form. All it is a function. Let's see, f of x, y, z, or however many variables you have. We'll stick with 3. All right. That's all there is to it. It's just a starting point, really. Okay. Next, a 1 form is a 0 form with dx, dy, or dz attached to it. So these 3 expressions, dx, dy, dz, we're actually going to start manipulating these now and performing operations on them that are a different character than what you're used to. These are called the basic 1 forms. So for instance, I'll often use Greek letters to refer to differential forms. So omega, for instance, well, an example would be sine of xy dx, or eta is u dx plus z dz. So it's just a function followed by either dx or dy dz, and you can only have one of them, whichever one you want. Okay. Then we have a 2 form that has a function and 2 basic 1 forms. So we have, for instance, omega is x squared y plus yz dx dy, for instance. Or you can also add forms of the same order. I'll fill in another one here. Let's see, give me a Greek letter, rho. So sine x dy plus cosine z dz. So if you have forms of the same order, you can add them, like so. So each term is only going to have one of these expressions, dy or dz, in it. You cannot add forms of different order. That is not a well-defined operation. It would be u dx cosine y dz dx plus sine z cosine x dx dy. Right. So again, 2 forms. You can add 2 forms together. Now, the way 2 forms are customarily written, so the basic ones, we have dx dy, dz dx. By convention, we write the z first, and you don't absolutely have to, but that's just so we're kind of going in cyclic order here, and then dy dz. Okay. Notice in the 2 forms, whichever 2 we put together, they're always distinct. You don't absolutely have to do that. Two forms where you have dx, dx do arise, but we stipulate that those are 0, they're equal to 0. So if they come up, they just go away immediately. Finally, you have a free form. So that includes dx, dy, and dz. So it could be something like so this function times dx, dy, dz. So really, there's only one basic free form, and that says dx, dy, dz. Okay. So, in any of the integral theorems that I just erased, what you're integrating is a differential form. So if you're integrating over a k-dimensional region, what you're integrating is always going to be a k form. Because you'd expect to see something like this being integrated over a curve, or something like this being integrated over a surface, something like this being integrated over a solid. Okay. Now, this is where things start to get a little weird. Because we only have one operation so far in these forms, just adding them. But in order to really make use of these things, there's a couple other things that we need to be able to do. We need to be able to multiply forms together. Because you can think of this, for instance, as a product of the function sine of xy and the basic form dx. So concatenating together like that, you could think of as multiplying. We're going to define a multiplication operation for forms. And then, since we're interested in integrating forms, we need to be able to differentiate them. So we'll define a differentiation operation that takes into account not just ordinary differentiation of functions like you're accustomed to, but also how we handle these basic forms, differentiating with the dx, dy, and dz parts. Okay. So first, the multiplication operation.
Cell phones, gotta love them.
What? Oh. All right. So given two forms, call them omega and eta, of any order. I should mention that define forms from order 0 to 3. But if you have a function of more than 3 variables, you can define forms of higher order. So if x, y, z, and w, you can define a 4 form. It has dx, dy, dz, dw. We're not going to do that here, but you can. So if you have two forms of whatever order, they don't have to be the same. Okay. The wedge product of omega and eta, we write it this way: omega, the little wedge there, multiplication, and eta. So this is how we write the multiplication operation, or you can think of it as omega eta if you want. So how does this particular multiplication operation work? Now, if omega and eta are 0 forms, they're just functions, then it's standard multiplication of functions, so there's nothing different there. But it's when you work in everything else that things start to get a little strange. All right.